everyone, welcome back to Markov processes. When we last left off, we were talking about positive recurrence and null recurrence for states of a Markov chain. So let me back up just a little bit and talk about recurrence again. A state of a Markov chain is said to be recurrent if the Markov chain starting from that state will return to that state in finite time with probability 1. But if there's any chance, large or small, any amount of probability that you will not return, the state is said to be transient. Now, we proved that recurrence and transience are class properties. And by this, I mean communication class properties. And by this, I mean that if you have a state that is, for example, recurrent and it communicates with another state, so maybe not in one step, but there's a way to get to another state and a way to come back again, then the other state must also be recurrent. The same it can be said for transient. So if you have a state that's transient and communicates with another state, the other state must also be transient. Now, if you have an irreducible chain, that means that all states communicate and there's only one big communication class. In this case, all states of the chain are either recurrent or transient. And if all states of the chain are recurrent, we say that the chain is recurrent. If all states are transient, we say that the chain is transient. And when I talk about a recurrent or transient chain, it usually to me means that it's irreducible, but technically it doesn't have to be. So here's an example of a Markov chain with a reducible state space. I've got states 1, 2, 3, and 4. States 1 and 2 communicate, states 3 and 4 communicate, but there's no way to get between those two communication classes. However, for this chain, all states are in fact recurrent. There's no drifting away from a state. So you may never hit a state of this chain depending on where you start. If you start at state 2, you're going to be at state 2 or state 1 forevermore. You'll never hit states 3 and 4. That doesn't mean that states 3 and 4 are not recurrent, even though you can never hit those states. So the definition of recurrence implies, for a state, implies that you're starting at that state. So again, if I start at 1 or 2, I'll never hit 3, but 3 is recurrent because if I start at 3, I will eventually return to 3 in finite time with probability 1. But I'm digressing a little bit. What I'm trying to say here is that this chain can be said to be recurrent because all states are recurrent, and yet it's not irreducible. But I was saying that usually when people talk about a chain being recurrent or transient, it's kind of almost implied that it is that way because all states are communicating, although that is not the definition. So maybe I made that more confusing than it needs to be. There will be no question in this course. I will never just say a chain is recurrent and expect you to believe it's irreducible. If I mean for it to be irreducible, I will say that as well. So recurrence and transience, there's the review on that. And at the very end of the last video, we started to define recurrence. We broke it down a little further into, we would define a recurrent state as either being positive recurrent or null recurrent. And informally, this means like fast return versus slow return. But formally, a recurrent state is positive recurrent if the expected time to return is finite, and it's null recurrent if the expected time to return is infinite, which sounds a little crazy because the state has to be recurrent in order to be null recurrent, and a state is recurrent if you will return in finite time with probability 1. But if it's null recurrent, I'm saying the expected time to return will be infinite. Now, I don't think I can ever convince you or even me of the intuition behind that, but we did, in fact, see in the last video why that could happen mathematically, because we wrote the probability of returning in finite time as a sum of individual probabilities, and it's possible for that sum to be 1, but when you want to compute the expected time to return, it was a very similar sum of the same probabilities, but with coefficients in front of each probability. And so those coefficients are making the individual terms in that infinite sum larger. So you can see why that sum could potentially diverge to infinity, even though the sum without the coefficients is finite and is equal to 1. So returning in finite time with probability 1, does not necessarily mean the expected time to return to finite, which I know sounds really bizarre. But if the expected time to return is finite, that recurrent state is positive recurrent. Otherwise, it is null recurrent. I'm not going to prove it in here, but positive recurrence and null recurrence are also class properties. So if a state is, for example, positive recurrent and it communicates with another state, that other state must also be positive recurrent. If the state is null recurrent and communicates with something else, the other state must be null recurrent. The state is transient and communicates with something else, the other state must be transient, and so on. So if you have one communication class, if the state or the chain is irreducible, the whole chain must be recurrent or transient. And if it's recurrent, the whole chain must be positive recurrent or null recurrent. If you have a Markov chain on a finite state space, there has to be at least one recurrent state because there's no way to escape all states forever and not return. There's just nowhere to go with a finite state space. So at least one state is going to have to be recurrent. So if you have a Markov chain that is irreducible and on a finite state space, the finite state space says you need at least one recurrent state. Irreducibility says they're all recurrent. So that means the entire chain must be recurrent. Again, irreducible Markov chain on a finite state space must be a recurrent chain. And we can actually show that it must be positive recurrent as well. But we're not going to do that. Or I may come back in the future in this course, but it's going to be the distant future when I finish this course and put in like appendix videos to show things like this. But I am going to skip it here so we can do more interesting things because showing showing that is not fun and it's not illuminating. You're not going to get anything out of that proof that's going to help you with anything else. Okay, so we have been talking, at least in the last video, if not the last two videos, about a random walk. Now, there are many different flavors of a random walk, but we had the most sort of basic random walk, and that was we had our state space was all integers, positive and negative, and at each time step, our chain could move either up one or down one with some probability p and 1 minus p respectively. So there was no staying flat. For example, if you're at state one, you can't be at state one in the next time step. You're either going to be at state two or state zero. And there was no jumping up by two at a time or three at a time or anything like that. Now, we showed last time that if p, the probability of moving up by one, is greater than 1/2, then what's going to happen is the chain is going to drift off eventually to positive infinity. And we saw that in this case, all states are transient. So if you start at a state, you will eventually not get back to that state. And it's not as cut and dry as some of our finite examples where we had distinct communication classes where you can move away and it's not possible to get back. In this random walk with p greater than 1/2, we had transients. We have all states communicating as long as p is not strictly 0 or 1, but we just drift away. There's so many states and we drift off to positive infinity in that case, and we can't return to a starting state, or there's some positive probability that we won't. So when p was greater than 1/2, our random walk is transient. If p was less than 1/2, we also saw the random walk was transient and we will be drifting off to negative infinity. We did show that when p was equal to 1/2, so we have that balance of moving up and down, this was the case where the random walk is recurrent. And I claim that when p is 1/2, this is the case where the random walk is recurrent. However, you could drift away. Let's say we're starting the chain at state 0, and we go up with probability 1/2 and down with probability 1/2. And let's say we're driving that chain with fair coin flips. So I have a fair coin, I flip it. If I get heads, I go up by one. If I get tails, I go down by one. Now, if you flip a fair coin 10 times, it's not impossible or even that unlikely. You may get, say, 7 heads in 10 flips. So that's going to mean your random walk chain running according to those coin flips is going up more than it's going down. So maybe as you move, your random walk chain starting from, say, 0 hits state 10. That's not impossible by any stretch of the imagination. Once you hit state 10, the one half probability makes the chain want to hover there around state 10. It wants to balance it out, and it's difficult to come back down to state 0. And so we proved in the last video that when p is one half, the random walk is recurrent. I claim that because of how difficult it is to return to states in the case that you drift away, the random walk as we have defined it is actually null recurrent. So starting at any state, let's say state 0, the expected number of steps to return is actually infinite. This is something I do want to show, but I don't want to waste our time on right now. So if this were a live class, this would be something where I'd say, let's move on. I'll type it up. You can check it out later. And I will be putting one of those appendix videos into this series, not at the very end, like I talked about with some other things. I'll do it sooner rather than later, but it's also not my focus right now. I do want to keep the momentum of the course going. So I will eventually prove to you that the random walk as we have defined it with p equals one half is actually null recurrent. And I'm going to do that using something known as generating functions. And defining that and proving this is going to take an entire video. And I don't want to sort of stop our course right now. So I will be coming back to put in an appendix video eventually. But let's move on. So, this whole discussion really started with us looking at powers of a transition matrix. We had a weather chain, I believe it was, where our states were sunny, cloudy, and precipitation. And the transition matrix looked like this. And I started taking powers of this matrix and got to the 10th power. And we know by the Chapman-Kolmogorov equations that if you do that, the ijth entry of the matrix is the probability of moving from state I to state j in 10 steps. So we denote that matrix with a p super 10 in parentheses to say this is the matrix of 10-step transition probabilities. But we proved using the Chapman-Kolmogorov equations that this is exactly the same as taking the original transition matrix and raising it to the 10th power. So those are those two different notations here, but we got this matrix. And what we noticed is that within any column, the rows seem to be settling into being identical numbers. So looking at this first column, all of these numbers seem to be about 0.2306 something. Actually, we even have another digit where they're all the same. And what this is saying is that no matter where you start this chain, whether it's sunny, partly cloudy, or in the precipitation state, after 10 states, you will be in the sunny state with approximate probability 0.2306, no matter where you start. And you'll be in the cloudy state with approximate probability 0.239-ish. You'll be partly cloudy with approximate probability 0.375, etc. Now, these four numbers add up to 1, and what we're seeing is a distribution on the state space of this chain. We're seeing probabilities assigned to sunny, partly cloudy, and precipitation that seem to be long run probabilities of finding the chain in various states. I know 10 steps does not seem very long, but we are seeing us settle into what is called a limiting distribution. And the number of steps this takes for a given chain could be a lot longer than this, but we're seeing this chain settle down kind of quickly. So our goal, again, is to figure out when a limiting distribution will exist. And also, I kind of care about, for reasons you'll see eventually, that the limiting distribution does not depend on the starting value of the chain, which is what we're seeing in this matrix. We've been working towards a theorem that will give us sufficient conditions for this limiting distribution to exist and not to depend on the starting value of the chain. And we've been defining things like recurrence and null recurrence and transients. I have one more thing to define for you today, and I promise we'll finally hit that theorem. Okay, so in the random walk, we noted that starting at state 0, we could only return in an even number of steps. And that is true for any state for that chain. We say that every state in that chain has period 2. But let me define this more formally. The period of a state I in a Markov chain is defined to be the greatest common divisor of all integers n greater than or equal to 1, for which we can go from I to I in n steps with positive probability. So if you can return to a state in 3 steps and 6 steps, but not one or two, and let's say only 3 steps and only 6 steps, and you can't find other ways to return, just to make this easier. The greatest common divisor of 3 and 6 is 3, so the period there would be 3. Now, in our random walk example, we can return starting at any state, we can return in 2 or 4 or 6 or 8, we can return in actually any even number of steps and no other way. So we can't return in 7 steps or anything like that. The greatest common divisor of all of these numbers of steps that we can return in for the random walk is 2. So the period for each state of the random walk, as we have defined it, is 2. So I have a theorem for you, and that is that periodicity is a class property. Now, I haven't defined periodicity. What I mean by this is that if a state I communicates with a state j, then they both must have the same period. I don't know how you feel about this. Some people think this is obvious and clear. Some people don't. Some people actually change their minds after a while because if I could, starting at I, only return in multiples of 3, for example, but I can get to another state j, maybe I can go from j to j in some strange number of steps that will break the multiples of 3. So I don't know how you feel about this. Some people think it's really clear. Some people do not see it at all. Some people sort of go back and forth. So let's just prove it so that we know for sure that this is a true statement. To prove this, I want to use the concept of an integer dividing another integer. So recall, or maybe this is your first time seeing it, but if I have positive integers a and b, we say that a divides b if a goes evenly into b with no remainder, i.e., b is just a multiple of a. And this means that there must exist an integer k greater than or equal to 1 such that b is equal to a times k. So if a divides b, we write a and then a vertical line b. So this is read a divides b. Now note that if a divides b, b is necessarily greater than or equal to a. For example, 3 divides 9 because 3 can go into 9 an even number of times, not an even number, but with no remainder. But 9 does not go into 3. That's already a fraction right there. And there's a fractional remainder. So if a divides b, b must be greater than or equal to a. Now 9 does divide into 9 nice and evenly. It divides in one time with no remainder. So again, if a divides b, b must be greater than or equal to a. But if b also divides a, then a must be greater than or equal to b. And this forces a and b to be equal. And this is how we're going to show this periodicity claim. I'm going to show that if I communicates with j, the period for I will divide into the period for j, and the period for j will divide into the period for I. And that means that they must have the same period. Let's do it. I want to set up some notation. So consider states I and j that communicate. I'm going to let d sub I denote the period for state I, and d sub j denote the period for state j. Again, I want to show that di divides into dj and vice versa, and then we're done. Now, because I communicates with j, we know there exist integers n and m greater than or equal to 0, such that we can go from I to j in n steps with positive probability, and from j to I in m steps with positive probability. Note that the probability we go from j to j in n plus m steps. Now, can this happen? I'm claiming this can happen with positive probability, and you may be able to go from j to j in n plus m steps in many ways, and many ways that do not involve I at all. But one way you can do this is to go from j to I in m steps, and then go from I to j in n steps. So the probability of going from j to j in n plus m steps is greater than or equal to, because there may be other paths, the probability of going from j to I in m steps, and the probability of going from I to j in n steps. So this represents the probability of taking I would say one particular path, but this actually could involve many ways of going from J to I in M steps. Who knows what's going on in between? But we're seeing that independent increments property of a Markov chain because starting from J, if you hit I in M steps, now you're starting at I. So where you go next doesn't depend on, where you came from, and that's why we get to multiply these probabilities. But I think I'm making this sound too hard as well. You can go from J to J in N plus M steps in at least one way here. And that's why this probability is greater than or equal to this probability. And both of these are strictly positive because that's how we chose the integers N and M. So we know that this probability is strictly positive. And what does this mean? I can go from J to J in N plus M steps. Now, the period for state J, D sub J, is the greatest common divisor of all integers that for which I can go from J to J in that number of steps with positive probability. We now know that the period for state J, D sub J, must divide N plus M. Okay, so now seemingly unrelated, take any positive integer k such that you can go from I to I in k steps with positive probability. And I do mean a strictly positive integer here, so k is not allowed to be zero. I know I can always go from a state to itself in 0 steps with probability 1. But if k here has to be greater than or equal to 1, how do I know I can find such a k? Because I'm about to base a proof off of having such a k. So how do I know I can return to state I in some positive number of steps with positive probability? Because I never set this up to be a recurrent chain. So starting from I, can I return with some positive probability in a positive number of steps? We know that such a k exists because using what we just did at the end of the previous slide, I know I can go from state I in n plus m steps in at least one way. I can go from I to j in n steps and then j back to I in m steps, which again encompasses maybe more than one way because traveling between I and j in n steps could happen in many different ways. You can visit all sorts of different states. But this means that the probability of going from I to I in n plus m steps is greater than or equal to this sort of not one path, because who knows what's going on between I and j in these steps, but one way, I guess, going from I to j in the first n steps, which could happen in many ways, and going from j to I in the remaining m steps. And those are both positive probabilities. So this product is strictly positive. So here I've exhibited an integer n plus m for which I can go from I to I with positive probability. So there's at least one. I'm going to let k be any one of these integers, any one of these such integers. Okay, now let's consider the probability of going from j to j in n plus m plus k steps. This is greater than or equal to the probability of going from j to I in m steps, and then I to I in k steps, and then I to j in n steps. All three of these strictly positive. So what I have is the probability of going from j to j in n plus m plus k steps is strictly positive. So the period for state j, dj, must divide this integer right here. dj divides n plus m plus k. Now, we already said that dj divides n plus m, and now we're saying it divides n plus m plus k. So because dj divides n plus m, then there must be an integer, say c1, such that n plus m is this multiple of dj. It's equal to c1 times dj. And there must be another integer c2 such that n plus m plus k is equal to c2 times dj. If you take these two equations and solve for k, you'll see that k is equal to c2 minus c1 all multiplied by dj. And because k is strictly positive, n plus m plus k is greater than n plus m. And so c2 is guaranteed to be strictly greater than c1. So this is a positive multiple of dj. In other words, k was taken to be an arbitrary number of steps that we can go from I to I in with positive probability. And it is a multiple of dj. Now, because k is a positive multiple of dj, we know that dj divides k. But k was chosen to be an arbitrary number of steps that we can go from I to I in with positive probability. How do you find the period for state I? You look at every such k and you want to find the greatest common divisor. We just showed that the period for j, dj, is going to divide any of these possible number of steps. And so dj is going to have to divide the greatest common divisor of all such k that we can move from I to I with positive probability. This means that dj divides di. In other words, the period for state j must divide the period for state I. Now, that's half of what we want to show, but there was really nothing special about how I started looking at state J and coming back. So you can really reuse the proof. You don't even need different integers for n and m. You can reuse those integers. Um, the k integer might be different, but it is an identical, I won't even say symmetric, it's almost an identical proof here to show that di divides dj. Therefore, we do have that di equals dj. The period for state I is equal to the period for state j, which is what we were trying to show. So periodicity is a class property. Now, a Markov chain where all states have period one is said to be aperiodic. And just like I was talking about at the beginning of today's video, this is usually talked about in the context of irreducibility, but technically, we do not need to have an irreducible chain to talk about an aperiodic chain. So, strict definition, if every state in the state space has period one, the chain is aperiodic. But if you do have an irreducible chain and one state has period one, they will all have period one, and you will have an aperiodic chain. Quick example, suppose the state space is 0, 1, 2, 3, and 4, and we have a transition matrix that looks like this. I claim that this chain is aperiodic. It is not hard to convince yourself. I'm not going to walk through all the paths, but it's not hard to convince yourself that all states communicate. For example, I can't go here from state, say, 3 to 1 in one step, but I can get from 3 to 1 and I can get from 1 to 3 in some number of steps. So trace through if you need to, but convince yourself that this chain is irreducible. This means that all states will have the same period because we just showed that periodicity is a class property. So let's try to find the period for any given state. Now, if you look at state 0, I can't go from 0 to 0 in one step. That that doesn't mean anything for periodicity or whether or not it has period one. It just means we're going to have to sort of search a little deeper. So if I could go from 0 to 0 and say 2 steps and 3 steps, I already know the greatest common divisor there is 1. So no matter how many other numbers of steps I can go in, the greatest common divisor is going to be stuck at 1. But the easiest way to figure out what's going on here quickly is to note that I have a non-zero entry on the diagonal right here at 2. I can go from 2 to 2 in one step. This automatically means the period is going to be 1, because if I can go from 2 to 2 in one step and then maybe only in 4 and 8 and multiples of 4 or something like that, I'm going to be looking at the greatest common divisor of 1 and 4 and 8. The greatest common divisor is already locked in to be 1. So I can see pretty quickly from this entry being non-zero that the period for state 2 is 1. And because the chain is irreducible, that tells me that all states have period 1 and the chain is therefore aperiodic. But again, if you want to convince yourself more directly for, say, state 0, look at how you can return to 0, in what numbers of steps you can do that. And once you see that the greatest common divisor is going to be 1, you don't even need to look at higher numbers of steps because that's not going to change the fact that the greatest common divisor is 1. Again, I know I've said this a few times, but if you could go from 0 to 0 in 2 steps and you could go in 3 steps, the greatest common divisor is 1. And then after that, if you could go in 10, 20, 30, only multiples of 10, you already have 2 steps and 3 steps and 10 and 20, 30. The greatest common divisor is already 1. And you don't have to look at, higher numbers of steps to figure that out once you know that the period is 1 by looking at some low numbers. Okay, so this is an example of an aperiodic chain. And with that, we are ready for the theorem that I have been teasing out for you for I don't even know how long it's been or the number of videos. I am going to label this theorem Theorem Pi 1. So, why am I calling it this? We're about to have a theorem that gives us sufficient conditions for a limiting distribution to exist for a Markov chain that is independent of where you start the chain. And there's going to be a whole sort of cluster of important theorems about this limiting distribution. And there's a lot of theorems in this course. So, um, rather than saying theorem one, theorem two, theorem three, I want these to be really special and separate. And I'm labeling it theorem pi one, and I'll have a pi two, pi three. And I'm using the pi for reasons that will become apparent shortly. So just bear with me. But right now it's a labeling system for a sequence of theorems, theorem pi one, pi two, etc. Here it is. For an irreducible, positive recurrent, and aperiodic Markov chain, the limit as n goes to infinity of the probability of moving from I to j in n steps, number one, exists, and number two is independent of I. So that's what we've been looking for quite a while now. I will prove this theorem for you, but it's not going to be today and probably not in the next video. It will be coming. It's not one of those appendix videos that I may get to one day. It will be coming, but it will take us some time to build up to the proof. So for the rest of today, let's look at what we're talking about here in action. For the precipitation chain with sunny, cloudy, partly cloudy, or precipitation, here is the transition matrix. So this chain is quote unquote clearly irreducible. All states communicate. It is positive recurrent because once you convince yourself it's irreducible, all states communicate. It's one big communication class and it's a finite state space. So we have proven that if the chain has a finite state space, it must have at least one recurrent state. And if it's irreducible, then all states communicate and all states must be recurrent. And I did claim that you would have that for positive recurrence as well. So really, it's finite state space and irreducibility that's giving me that this chain is positive recurrent. And we did prove that for recurrence, but I only claimed it for positive recurrence. So this chain is irreducible, positive recurrent, and aperiodic. You can see right away here that because I can go from, say, sunny to sunny in one step with positive probability, then the greatest common divisor of all numbers of steps I can go in is going to be one. And the period for the sunny state is one, and it's irreducible. So the period for all states is one, and that's how we define the chain to be aperiodic. Now we saw that this chain appeared to have a limiting distribution when we took the 10th power of the matrix, and that these probabilities seem to be independent of the starting value of the chain. I want to quickly look at another chain, just states 1, 2, 3, and 4, that is reducible, that block matrix we've already looked at. If you take higher powers of this matrix, and 10 time steps happen to work here as well, when I took 10 time steps, I saw things settling down. And we will eventually talk about the rate of convergence to this limiting distribution because for your Markov chain, it might take a million steps. So this is definitely something we need to talk about, and we'll get there eventually. But here I saw this behavior when I took 10. I took the matrix to the 10th power to get 10-step transition probabilities. What I saw was, and I rounded here just to fit it on the slide, numbers that appeared to be the same for being in state one if you start in state one or two. What I'm seeing here is that if you start in state one or two, it appears that you will settle into state one with approximate probability 0.375 and settle into state two with approximate probability 0.625 and state three with probability 0 and state four with probability 0. So like these numbers are forming a distribution on the state space 1, 2, 3, and 4. And so I do see kind of a limit. However, it is not independent of the starting state of the chain because if we start at states 3 or 4, we're settling into a limiting distribution that assigns to states 1, 2, 3, and 4 respective probabilities 0, 0, approximately 0.667, and approximately 0.333. So for this example, kind of seeing a limiting distribution, but a different one depending on where we start. Now the theorem which I just stated, theorem pi 1, gives us not only a limiting distribution but it's going to be independent of the starting value of the chain. And you can see that in this case, the irreducibility criterion is failing. And that's one of the things we needed, not necessary, but sufficient to get what we want. So this chain is not irreducible, it is reducible. So it fails one of our sufficient conditions for having this limiting distribution being independent of where we're starting. And that's something you will tend to see when you have a reducible chain. Okay, so back to the theorem. Irreducible, positive recurrent, aperiodic. These are sufficient conditions, not necessary, but sufficient to give us a limit as we go of the probability of going from I to j in n steps as n goes to infinity, existing and being independent of I. Now, assuming this exists, I am going to call this limit pi sub j. So now you can see the pi coming in for the name of the theorem, Theorem Pi 1. And as this notation suggests, there's no I in it, and that's because this limit is not depending on I. So I'm going to define pi sub j to be the limit as n goes to infinity of the probability of going from I to j in n steps. This is itself a probability because these numbers here are all probabilities. They're all between 0 and 1. And when you take the limit, you're going to get something between 0 and 1. So I claim that this pi j is a probability. But real quick, let's draw a picture. So suppose you start a chain here, and maybe in one time step you move here, and then in the next time step you move here, and maybe you move here. If you keep following this to time infinity, you will end up somewhere. And if you start again, let's even start from the same exact state. Maybe this time you stay flat in one time step and move here, and then maybe you go down and move here and jump up and move here. And in the end, at time infinity, maybe you come in and land here. So before I landed kind of up here, now I'm landing here. And this probability pi j is the probability that you land in any given state j over here. Now, I just said that pi j is a probability, and I claim it's actually a probability distribution on the entire state space. So what I mean by this is number one, all of the pi j's are between 0 and 1 inclusive for every j in the state space. And this is because, again, it's a limit of numbers between 0 and 1. And if you sum the pi j over all j in the state space, let's just write out our definition of pi j here. This is a sum over j of a limit. I'm going to interchange the limit and the sum, which does require some care, which I've already said I'm going to kind of ignore in this course. If you've had more analysis, you might want to convince yourself of why you can do this, but I don't want us to worry about such things. It is important mathematically, but I want to stick to more of the Markov stuff here. So if you interchange the limit and the sum, which is definitely not a problem for a finite sum, but could be a problem for an infinite sum, then I get the sum over all j in the state space of the probability of going from I to j in n steps. Now, this is summing across the ith row of the n step transition matrix. But starting from I, you have to be somewhere in n steps. These probabilities have to add up to 1. So this is the limit as n goes to infinity of 1, which is 1. All the pi j's between 0 and 1, when summed over the entire state space, they sum to 1. So the collection of the pi j's form a probability distribution on S. If the state space is 1, 2, 3, 4, you've got a pi 1, pi 2, pi 3, and pi 4, which are assigned probabilities for all the states in S. Okay, so notation. We're going to use a pi alone without a subscript to denote the entire collection of probabilities or the name of this distribution. So I might just start off by saying, suppose this Markov chain has limiting distribution pi. That means that there's some pi 1, pi 2, pi 3, or, even though we're dealing with discrete state spaces, we do not need to be on integers, but there's some pi's assigned to each value in the state space. But I'm going to use pi without a subscript to just be the name of the distribution or to talk about the collection of all of these probabilities. And another notation is we're going to use pi with a vector over it to denote a row vector of the pi j. So in the example that the state space is, say, 0, 1, and 2, pi with a vector over it is going to be the collection, or row vector, sorry, pi 0, pi 1, and pi 2. And it's going to be important to use a row vector here, or you could use a column vector here, but Most people use row vectors, and we need to decide on something and kind of fix that. So that's what I'm doing now. It's going to be a row vector. Whew. We finally have our first big theorem pi 1, which gives us sufficient conditions to have a limiting distribution and to have it be independent of where we start the chain. I am going to break from limiting distributions for a bit right now and talk about something seemingly completely unrelated. In fact, it's not going to be unrelated at all. But to avoid confusion, let's just imagine we're breaking from that right now to talk about something completely different and forget about limits. I'm going to let xn with brackets as n goes from 0 to infinity denote a Markov chain on a discrete state space S. So suppose I have probabilities associated with suppose I have an initial distribution for this chain. So the probability that x0 is one value in the state space versus another. And usually we're talking about integer values, but it does not have to be the case. So I'm going to take a whole collection of probabilities. I'm going to call them P sub I, lowercase p sub I, where I is in S. I'm going to throw some brackets around this. So this is the collection of all P sub I such that I is in the state space S. I'm going to let this denote my initial distribution for the chain. So P sub I is the probability that the chain at time 0 is in state I for any I in the state space. Given an initial distribution like this, we know how to find the distribution for the chain at time 1. We've done this already, but as a reminder, for a nice simple state space like 0, 1, and 2, if you want the probability that x1 is equal to state j, you would condition on where the chain was at time 0. And we have an initial distribution for the chain, so you would get that this is the probability that x1 is j, given that x0 was 0, times the probability that x0 is 0, plus the probability that x1 was j, given that x0 is 1, times the probability that x0 is 1, plus the probability that x1 is j, given that x0 is 2, times the probability that x0 is 2. So we condition on where the chain was at time 0. This, and this, these are the definitions of lowercase p sub 0, p sub 1, and p sub 2. These are one-step transition probabilities. So this is P sub 0j, P sub 1j, etc. And we get this. I didn't really need to make the state space so simple for us to write this down. Let's just do it more generally. So given that initial distribution for the chain, the probability that at time 1 the chain is in state j can be written as the sum over all I in the state space of that probability, given that x0 is I times the probability that x0 is I. Our notation for this, lowercase p sub I. Our notation for this, lowercase p sub ij. And this, I don't know what this is. This is a probability. We could give it a name, like maybe q sub j, or maybe p sub j tilde, because it's not necessarily the same as these p sub i's over here. We do have a p sub j, and I'm not saying that the probability that the chain at time 1 is in state j is equal to p sub j. P sub j is the probability that at time 0 we were in state j. But what if they were the same? What if we could choose that initial distribution or those initial lowercase p sub i's in just the right way to balance things so that we see the same distribution at time 1? If you imagine, let's draw a picture here. So a time axis, a state space axis, maybe we start a chain here, and we don't just start it arbitrarily here, but we choose a value drawn from a given distribution. So maybe the distribution looks like this. So this is telling me that I'm going to start over here a lot. I'm going to start here and here next most often. I'm not going to start here very often, but with some small probability. And if I move forward to time 1 using the transition probabilities, maybe I end up here. And if we started all over with a value drawn or even simulated or just in theory coming from the distribution represented by this histogram, maybe now it's over here because there's a high probability of being over here. And if we run it forward using the given transition probabilities, maybe now we end up here. Now I have 2 output points. And if I do this again and again and again and collect the output at time 1 and look at a histogram of values, I will see a shape here as well. And I'm hoping the shape will be the same. If I choose the starting distribution in the right way, I can get the distribution at time one to look the same. Okay, so with that, I want to define such a special distribution. I have a Markov chain on a discrete state space S, and we looked at the probability of finding the chain in state J, given we started in state I, and it looked like this. I did have these two values, flipped, but it doesn't matter. I'm just multiplying. And I wanted this probability to match these probabilities. Now, this is the probability of starting in state I. This is the probability of being in state J. So this would be a piece of J if we had a special enough starting distribution. It's so special, I want to give it its own name and not just use the letter P. Let's define such a special distribution. A distribution pi on S. So pi is going to be a collection of individual probabilities, pi j for all j and s. And this seems like a poor choice of notation because I've already used pi for another kind of special distribution, a limiting distribution, but it's going to turn out to make sense. So forget that we ever talked about limiting distributions. Right now, I'm going to use pi to denote a collection of probabilities, pi j for all j and s, and it's going to be known as a stationary distribution for the chain. If I call this up here pi I, if this is going to be pi j, a probability coming from the same distribution. So if it satisfies the equation, pi j equals the sum over all I and s of pi I, pi j. This is known as the stationary equation for a stationary distribution. And the word stationary is not changing in time. That's what it's referring to. We're seeing the distribution not change in time. Now, by the way, if we could start a value with a draw or value from this special distribution, i.e., we're going to start here most often and here not so much, and here and here and here according to these given probabilities represented by heights. We did already say that we're going to see the same distribution in the output if we collect the output over and over and over again at time one. But if the output collected over and over and over again at time one is coming out in the right probabilities, then the output at time one is like a draw from the stationary distribution. So if you went forward again to time two, then you should see that distribution maintained, because starting at time zero with a draw from the stationary distribution is just producing a draw from the stationary distribution at time one, which is like a starting value when you move from time one to time two. So if we do this over and over and over again and keep running sample paths starting at time zero out to time two and collect the output, we should see the same shape again. That's stationarity. The shape is not changing in time, it is stationary. Okay, so if pi is a stationary distribution for the chain, by definition, pi j is the sum over all I of pi I pi j. But I claim that we also have that pi j is the sum over all I of pi I pi j super n. So starting from zero, if you went out for a fixed number of time steps, like 10 steps, then you would find that same shape at time 10 if you redid the whole sample path over and over and over again, starting at different values, not the same, but values drawn from the stationary distribution. And this is going to be true for any fixed integer n greater than or equal to 1. I don't want to muddy the waters right here, but we might find ourselves going forward for some random number of time steps where you say run the chain until something specific happens that will happen with some kind of random occurrence. And then that could actually mess up this equation. I don't want to get into that right now. We'll talk about that eventually. But for any fixed positive integer n, this equation should hold. Given that this equation holds, let's prove it. We're going to prove it by induction on n. So I'm going to let pi be a stationary distribution. And we want to show this. Now, by definition of stationarity, this holds when n equals 1. And for induction, I'm going to assume that this holds for any given positive integer n. And we want to show that it holds when you replace this with an n plus 1. And then we're done with our inductive proof. So let's write this down with n plus 1 up here. And I am going to use the Chapman-Kolmogorov equations to rewrite this probability. I could rewrite it in so many ways. including through the Chapman-Kolmogorov equations. I can break this up in many ways, and I may still actually get my proof done. So I'm going to pick away. I'm going to write the probability of going from I to j in n plus 1 steps as the sum over all intermediate states k in the state space of the probability of going from I to k in one step and then k to j in the remaining n steps. Now I'm going to reorder these sums, and that will have the k sum on the outside and the I sum on the inside. And so I want to sort of collect all the I terms next to the I sum, and we get something that looks like this. But this right here is the right-hand side of our stationary equation. Now, I don't have a j where I had a j, I have a k now. But if you look at your stationary equation, this is by definition pi sub k, because we are assuming here that pi is a stationary distribution. So we end up with the sum over k of pi sub k p kj super n. And if you go back to the previous slide, we made the assumption that the sum over I of pi I pij super n is equal to pi j. This is the same thing, but with k's, and we're summing over k. It doesn't matter that there's a different letter here. This is equal to pi j by our assumptions stated on the previous slide, our second step in induction. We said the stationary equation holds for n equals 1, and we assume that it held for a general n, and that's what I'm using right here to conclude that this is equal to pi j. This to this is what we're trying to show. So we have finished our inductive proof that if you have the stationary equation holding for one time step, it will hold for any fixed number of time steps. Again, think back to the picture with the sideways histograms. If you start at time 0 with a value drawn from this special distribution and run forward some fixed number of steps, collect the output, start all over, do it again and again and again, the output, make a histogram, it's going to be forming the same shape. That's what a stationary distribution is. So I used pi's for limiting probabilities. I let pi j be the limit as n goes to infinity of pij super n. And now I use them for stationary probabilities, where I said that pi j is equal to the sum over all I in the state space of pi I pij. That doesn't seem like a very smart thing to do if I'm trying to use these pi's instead of p's. They are the Greek letter p's to be very special probabilities. But the reason I'm doing this is because these two kinds of distributions are really closely linked. I claim that any limiting distribution is automatically a stationary distribution. Let's prove it. Suppose that pi j has been defined as the limit as n goes to infinity of pij super n. Again, I'd like to remind you that this limit does not depend on I. So I will also get pi j if I take the limit as n goes to infinity of, say, p kj super n. In other words, I can put any letter in here for the first subscript. So keep that in mind. Now I want to show that this pi j, as defined this way, forms a stationary distribution. So I'm going to take the right-hand side of the stationary equation as I've written it. You may be writing it the other way. And look at the sum over all I in the state space of pi I pij. And I'm going to plug in the definition for pi I. Okay, so the pi j, the j here has to be the final subscript on the p over here. So I can use an arbitrary starting subscript. So I'm going to write pi I as the limit as n goes to infinity of p k I super n. So this is an I, and this is an I, and this is anything. I decided to make it a k. Now I'm going to do the same thing we've been doing a few times now in today's video. I'm going to interchange the limit and the sum. And I'm left in here with a sum as I runs over the state space of pki super n pij. So by the Chapman-Kolmogorov equations, this is the probability of going all the way from k to j in n plus 1 steps. I've got the limit as n goes to infinity of pkj super n plus 1 in parentheses, but it's a limit. Who cares if I went one time step faster? If this exponent goes to infinity, as n goes to infinity, it certainly goes to infinity as n plus 1 goes to infinity. So by definition up here, and just maybe adjusting subscripts, this is pi j. This is the limiting probability of ending up in state j as n plus 1 gets really, really large. So go from here to here. This is the stationary equation. So starting with this assumption, we have shown that these pi's satisfy the stationary equation and the distribution pi is stationary. So I'm almost out of time. I want to show a quick example. You know what? Maybe it's not worth starting. So in the next video, I will have a lot more numerical examples. I'll be less theoretical than we were in this video. We'll look at several examples of finding stationary distributions and limiting distributions, and look at some pretty cool problems. And we will find limiting distributions exactly without having to take powers of a matrix and saying that looks like it's settling down. So I always love the theory, but I will have the next video be more example driven than this one. So I hope to see you there next time on Markov processes.